Hi, my name is Mike Archbold.
My name is Brandon Fry.
My name is Devin Pelkey, and
We are the Group 22 UAV team. Today, we will be discussing our senior design project, which was to design and build an autonomous UAV, or unmanned aerial vehicle. This UAV utilizes an onboard camera, as well as autonomous navigation and flight systems to be used for surveillance purposes by Hatfield Company.
throughout this video, we will be discussing two main topics. First, the project overview, which we will discuss the function of the UAV and the three main subsystems that make up the UAV. And second, the system operation, where we will cover how to use the UAV in the field. The first engineering requirement is called battery level detection. The battery level detection requirement means that the UAV needs to be able to detect the battery level at any time in the flight, update the user of how much battery is remaining, and if the battery falls below a certain point, needs to return back to base to avoid any accidents. This requirement has been successfully passed. The second engineering requirement is called flight plan length. Flight plan length means that we need to have a user-defined flight plan of at least 10 coordinates. This requirement has been passed. The third engineering requirement is called flight plan organization. Flight plan organization means that the UAV needs to follow a user-defined flight plan of at least 10 coordinates and be aware of when it gets to each coordinate using the GPS. This requirement has been successfully passed. The fourth engineering requirement is called in-flight photos. In-flight photos means that there needs to be a camera module on board the aircraft that can take pictures of a 160 by 120 pixels and transmit them wirelessly back to the user interface, where it can be reconstructed on the GUI screen. This test has been successfully passed. The fifth engineering requirement is called landing takeoff. The landing takeoff requirement means that the UAV can autonomously take off and land with the push of a button. This test has been successfully passed. The sixth engineering requirement is called minimum height. The minimum height requirement means that the UAV needs to be able to obtain a minimum height of 100 feet and sustain flight at that altitude. Unfortunately, we are unable to pass this test because we did not want to send the UAV to that altitude before the engineering expo in case anything were to happen. However, we do have a working altimeter that can read the altitude greater than 100 feet with respect to the starting position of the UAV. The seventh engineering requirement is called open operating range. Open operating range means that we have to have wireless communication between the helicopter and the user interface of at least 1.5 miles in a line of sight situation. Unfortunately, we are unable to pass this requirement because the wireless communication modules that we purchased are unable to communicate at that distance. The eighth engineering requirement is called stall detection. Stall detection means that when the UAV, for some reason, ends up in a free fall or where it is no longer in control, the helicopter will be able to sense that and alert the user by sending it the most recent GPS coordinates so it can be retrieved. We were able to successfully pass this requirement. The ninth engineering requirement is called takeoff area. Takeoff area means the UAV needs to be able to take off in a 25 square foot window. We were able to successfully pass this requirement. The 10th and final engineering requirement is called urban operating range. Urban operating range means that we need to be able to wirelessly communicate between the helicopter and the user interface at a distance of 1/2 mile in an urban setting. We were unable to pass this engineering requirement because the wireless communication modules that we purchased were unable to communicate at that distance.
Thank you, Mike, for going over the system requirements with us. I would like to now discuss the main subsystems which make up the UAV. There are three primary subsystems, which include the main processor, flight controller, and GUI user interface. The first subsystem I'd like to discuss is the main processor. The main processor essentially acts as the brains to the UAV. It has many different features which allow it to act as such. The first main feature I'd like to discuss is its navigation capabilities. Utilizing the onboard sensors such as GPS, altimeter, and compass, it's capable of keeping track of its current location relative to the ground as well as home base. Another valuable feature of the main processor is its ability to communicate wirelessly to the GUI user interface. Utilizing the wireless communication system, it's capable of constantly updating the user interface as well as receiving new coordinates from the GUI. Another primary feature of the main processor is its ability to take in-flight photos. Utilizing the onboard camera, it's capable of sending wirelessly compressed JPEG images that are 120 by 160 pixels. The final feature of the main processor that I'd like to discuss is its ability to coordinate with the flight controller. It's capable of sending proper flight commands to the flight controller to ensure that the next coordinate on the flight plan is reached. The next subsystem I'd like to discuss is the flight controller. The flight controller's purpose is essentially act as the muscle for the helicopter. There are many features which allow it to act as such. The first feature I'd like to discuss is its flight stabilization system. Utilizing different sensors such as gyros and accelerometers, it's capable of keeping track of its current orientation as well as its acceleration in any of the three axes. The second feature of the flight controller I'd like to discuss is its ability to perform flight maneuvers. When it receives a command from the main processor, it's capable of performing that flight maneuver that's specified that's necessary to reach the next coordinate. The third feature of the flight controller I would like to discuss is its stall detection system. It's capable of detecting any stalls that occur to the UAV as well as perform countermaneuvers to pull out of any stalls. The last feature of the flight controller I'd like to discuss is the fact that it's autonomous. It doesn't require any user input in order to keep the helicopter in flight stable as well as perform any of the flight maneuvers required from the main processor. The last main subsystem I'd like to discuss is the GUI user interface. The GUI user interface essentially acts as an input system for the user. There are many features which allow it to act as such. The first feature I'd like to discuss is its customizable flight plan. The GUI allows the user to input at least 10 coordinates into the flight plan of which the helicopter will follow. The second feature that the GUI offers is its picture display. When a picture is taken by the main processor and transmitted wirelessly, the GUI recompiles the compressed JPEG image and displays it in-screen live. The third feature I'd like to discuss is its live updates. While receiving constant updates from the helicopter, it continuously updates different graphs and different data values to show the current orientation as well as speed and other valuable information about the helicopter in screen. The last feature of the GUI I'd like to discuss is its communication capabilities. It's continually able to keep up to date with the helicopter as well as send it updates on coordinates and flight plan changes while the helicopter is still in flight. While there are many different features necessary to make this helicopter work, those are the three primary subsystems that ensure that the helicopter is fully functional.
Thank you, Brandon, for going over the three main subsystems of our UAV. I'm now going to go over the system operations of the vehicle. This essentially allows us to perform a flight. The first thing that we want to do is verify that the Jesus bolt, which is located directly under this large white gear, is tight. And we can see that this is tight. The second thing that we want to verify that is tight is the clamp located directly under the cyclic. And we can see that it is tight as well. The third thing that we need to make sure is tight is all of the screws located on the helicopter. If any one of these screws is loose, the helicopter is liable to literally rattle itself apart. The final thing that we need to verify that is tight is a belt located at the top of the helicopter. This belt essentially allows the tail rotor to spin in accordance with the main rotor. If this is not tight, the helicopter will not be able to perform maneuvers that we expect it to. Now we are ready to add the battery. The battery is simply slipped over the front of the nose of the helicopter and plugged in. We just received a sound bite saying that the helicopter was ready for flight. We can also see that the LED, the blue LED, located on the flight controller and on the main processor is on, and those are working correctly. At this point, we are now ready to put on the canopy. And again, this is just slipped over the front and attached to the two posts on either side of the helicopter. At this point, the helicopter is ready to fly, and I'm now going to show you the graphical user interface. Once you have successfully plugged in the UAV transceiver into the computer, you are now ready to run the UAV program. On this particular computer, the program is located on the desktop. Once you have opened the program, on the left-hand side you can see that there is an initialization button, and this allows the computer to communicate to the transceiver. For this particular computer, it is on COM port 10. I will then open the port, and as you can see there's a few dialog boxes and an altitude gauge. This will be filled while in flight. I'm now going to go ahead and open the flight plan maker, and as you can see more boxes have shown up, and here you enter in the coordinate point that you would like the helicopter to go to. It is important that you enter the correct value in each dialog box, as if you were to enter a letter in a number field or a number in a letter field, once you try to add this coordinate point, it would not allow it, and it would ask you to go in and change the error. This elevation box is relative to the takeoff elevation. So I'm going to go ahead and enter 100 feet. The duration tells the helicopter how long to stay at that coordinate point. And on this checkbox it says take picture here, and on this particular coordinate point I do not want to take a picture at this coordinate point. I can then go ahead and add location to flight plan, and as you can see here it has entered it into the flight plan list. I actually only want to make the helicopter fly to this current coordinate point, so I'm going to go ahead and click Start Flight Plan, and this will then activate the helicopter in its flight sequence. And as you can see, the helicopter is now starting to take off.
Thank you, Devin, for explaining how to use the UAV. In this video, we have discussed the overall function of the UAV, as well as the three subsystems that make up the UAV in the project overview section.
We also reviewed how you would use the UAV out in the field in our system operations section.
After completing our senior design project, we have a few suggestions for next year's senior design team. Our first suggestion is ordering at least 2 of every component. We feel that this is necessary because it will minimize the delay caused by lost or broken parts. Our second suggestion is in regards to group dynamic. The only reason why we were able to succeed in our ambitious project was due to our strong group dynamic inside and out of the lab.
A third suggestion our group found was to start very early on your project. You'll find that you'll run into different factors while completing your project that will cause different delays, and you want to ensure that you have plenty of extra time to overcome these different delays. Another suggestion we found important was to seek professional opinions when dealing with unfamiliar modules. For instance, it was very valuable to our group to consult Rotary Motion Hobbies when determining how to use and maintain our helicopter module.
A fifth suggestion that our group has is to do research on several different of similar components before making any purchases. Though these components all accomplish the same goals, the way you interface with them and the way that they are used is different and may or may not work in your system. The last suggestion that we have is to come up with a problem-solving strategy early in fall term before you come into any problems. So once you do run into some problems, you'll know how to handle them and they will not cause much delay. Now that you have learned about our senior design project, we'd like to give a special thanks to the people that made this possible, such as Hatfield Company,
Rotary Motion Hobbies,
and Advanced Circuits.